Yes, students, I hope you're able to hear me, right? So we'll get started. See, the last concept that we discussed was based on terminal velocity, right? So I hope everybody remembers. We discussed about Stokes' law and terminal velocity, from which this formula has come. That V is equal to, what was the formula? V is equal to 2 by 9 r square g into rho minus sigma, the whole divided by beta. So where do we speak about terminal velocity? We mainly speak for what kind of fluids? What are the fluids for which we speak about terminal velocity?
Viscous fluids, sir.
Yes, it is viscous fluid. So we speak about terminal velocity for fluids which have viscosity associated. That is, when they have internal friction among their layers, we discuss about that, right? So now we are going to see the counterpart of it. That is, we are going to see what is meant by streamline and turbulent flow. So that's the concept we are going to start with today. So streamline and turbulent flows is the first topic of discussion. So first thing, let's understand what a streamline flow is. So if you have a liquid that is flowing such that each particle of the liquid passing through a given point moves along the same path and has the same velocity as its predecessor, the flow is called streamline or steady flow. So let me explain it. Let me explain what it exactly means. Okay. So what are they saying? When a liquid flows, okay, such that each particle of the liquid passing through a given point moves along the same path and has the same velocity as the previous particle, then that flow is called as streamline or steady flow. See, for example, if I have a tube, okay, imagine this like the tube from which you take out water, let's say for pouring or for plants. Okay, let's say you have a tube. Inside this tube, you have connected it to a tap, so the water is flowing through it. Okay, so water is flowing through it. So let's say your garden is on the right hand side and you have your tap on the left hand side. Okay, so water is obviously going to flow from tap to garden. So it is flowing from left to right direction, right? So this is the direction of flow. Now comes the next question. So how do you measure the velocity at every point? Remember, throughout science, okay, wherever you need to measure the velocity, at that particular point, you need to draw a tangent. And tangent should be drawn in the direction of flow. So when you draw it, that will give you the velocity of the particle at that particular location. If I say the velocity of the particle here is v1, if the particle, let's say it is reaching a point 2, here it will be v2. Guys, you're able to understand? So at every point, if you draw a tangent to that particular layer, then that tangent with the proper direction, that is the direction of flow, will give you the direction of velocity of that particular liquid particle. Clear? Now comes an important question. So when here we understood that the liquid is flowing, then how is it supposed to flow for it to be called as streamline flow or steady flow? It should flow in such a way that that a liquid particle, when it is passing through a given point, if I take this point, okay, if I take 1 and 2, if I take the point 1, then how many particles will keep reaching point 1 when you see from the left hand side? So this is at some instant, let's say t is equal to 0. Okay, try to understand this. This is the time I'm starting the stopwatch. At t is equal to 0, I'm able to see a particle with velocity v1 is crossing the point 1. After t is equal to 5 seconds, what would have happened? There would have been some other particle at the back, right, which is also moving along the same path. If let's say this point is 3, okay? If I try to calculate the velocity of the particle here, it is v3. Try to understand, guys. This is the velocity of which particle? Velocity of the third particle. So if the velocity of the third particle at point 3 is v3, what should it be its velocity when it is reaching point 1 after 5 seconds?
Should be V1, sir.
It should be v1. Okay. Similarly, when v3 is reaching point 2, how much should its velocity be?
V2.
v2 means whatever is a particle at the back, if you take a particular position, if I fix that point, whichever particle is coming from the back, okay, whichever particle is coming from the back, when it reaches that particular point, then it should have the same velocity as the previous particle had. Okay, here the previous particle is v2. So when v2 was at point 2, velocity was v2. Similarly, when the third particle is reaching point 2, its velocity should be v2. Am I clear? If this kind of a procedure is happening, then this motion is what is called as a steady flow or streamlined flow. Am I clear, guys?
Yes, sir.
Yeah. Make a note of it. Write it in the words you understand. Done. Let's go to the next concept. So this is what we call as streamlined flow. So, see, generally the word they use is steady flow. Why do they call it as streamline is because, see, generally you cannot see the layers of the liquid like this. Right? When I say water is flowing, it is going to flow like this. This is how water is going to flow. Right? So let's say the pipe is like this. So let's say this is the pipe. So within the pipe, you will see water like this only. Will you be able to see like lines like this? Obviously, no. Okay. So, but what we are doing is to try to understand the velocity of particle of water at each point. We are imagining that it is broken into different layers like this. Okay. And this is what we call it as streamline. You are able to see each line, right, which is bent. So each line is what is called as a streamline. And don't forget the fact that velocity of the particle at any point is calculated by drawing a tangent at that particular point. VA, VB, and VC. Clear? Okay. Next is a concept called as tube of flow. Name itself is suggested. A bundle of streamlines forming tubular region is called as tube of flow. See, for example, inside the tube, you're able to see the diameter, right, on the left-hand side. So inside this tube, what is going to happen is liquid is flowing. When you break it into multiple regions, then those layers all put together are called as streamline, and this collective diagram is what is called as tube of flow. So the bundle of all these streamlines is what is called as tube of flow. So the important point to be noted here is the boundary of such a tube is always parallel to the velocity of the fluid particles. No fluid can cross the boundaries of tube flow, and the tube behaves somewhat like a tube. In a steady flow, the shape of the flow tube does not change with time. Okay, so have this point in your mind. Next comes the important topic, which is called as turbulent flow. So this is only a theoretical concept. All we are going to deal in this chapter is completely with steady flow. Because turbulent flow is a little bit complicated subject. We will not be worried about it. So let's discuss about turbulent flow. Okay. So the definition is given like this. I'll tell you. When the liquid velocity exceeds a certain limiting value. So each particle has a velocity, right? So if the liquid velocity exceeds a certain limiting value, limiting means maximum value, which is called as critical velocity, the liquid will not flow anymore in the streamlined path like this. Rather, it will start flowing in a zigzag path. Okay. As a result of which, what will happen is the velocity of the particle will keep changing continuously. And it will randomly get changed, not like you can actually calculate it. It is very difficult to analyze this kind of a motion. So this kind of a flow is what is called as turbulent flow. Let me show you an example. See. You have two diagrams. So the first one, can you tell me, is it a streamlined flow or a turbulent flow? First diagram, second diagram. So first, look at the arrow marks. No, look at the way arrow marks are aligned. Is it a streamlined flow or a turbulent flow? Can at least just it is a streamline, right? It is a steady flow. Whereas if you want to visualize what is turbulent flow in reality, look at the liquid here. No? Some particles are moving this side, some particles are moving right. So they move in a haphazard way. When this kind of a flow takes place, that is what we call it as turbulent motion. I'm not sure if you have heard this word. If you go in flights, right, sometimes whenever there is a shake, a slight shake happens because of the wind. Have you heard that they say there is a small amount of turbulence?
Yes, sir.
Not you would have heard this, right? So that's the meaning actually. Okay, that's what we call it as turbulent flow. Anyways, our concept of discussion is not going to be about turbulent flow, but I wanted you to understand what it is. Okay, shall I proceed? So we will be concentrating on properties of streamlines. So first important point here, when you talk about a steady flow, you have streamlines, right? That those are parallel to the tube. You can take any two streamlines you want. Okay, in a steady flow, what will happen is no two streamlines can cross each other. And the reason for that is very simple, because if at all they cross each other, what would have happened? If I say first is like this, second is like this, this is the meaning of crossing. First streamline, second streamline. I cannot call this kind of a motion as steady flow, because at this point, how many tangents can I draw?
Could you repeat the question?
See, first one is there, right? This is the first diagram. The first diagram, if I take the first streamline, okay, at every point, let's say it is flowing from left to right. At every point on the streamline, how many tangents can I draw? At every point. So if I take one random point, at that one random point, how many tangents will I be able to define? Tangent is a line which cuts.
Sir.
No. If I take one point, see, this is how the streamline. I'm taking one of the streamlines, okay? If I want to find the velocity of this particle at this point, I put a red color dot, right? Liquid is flowing from left to right. If I want to find the velocity of the particle here, what am I supposed to do?
Yes, sir. One tangent, sir.
You can draw only one tangent at a particular point. So at a given point, you can draw only one tangent. throughout the streamline, you can draw infinite. In a similar context, so I'm talking about the first concept. I'm putting a tick here, right? I'm talking about the first concept when no two streamlines are intersecting. Whereas if they intersect, like in this case, then how many tangents will I be able to draw at that point? I put a dot, no? That is a point of intersection. So at the point of intersection, how many tangents can I draw?
One.
You can draw one like this, one like this. You can actually draw two tangents. So the meaning of these two tangents is the particle which is common to both the first streamline and the second streamline is having two velocities at the same instant. Is it possible?
Not possible, sir.
Any, like for example, you are going on a road. You can, if I calculate your speed at a particular instant, there should be only one speed associated, right? You cannot say at 5th second I had velocity of 60 kilometer per hour and 80 kilometer per hour. Not possible. At an instant, you will have only one velocity. So this is a very, very, very important point which comes for 1 mark. See, if I have to speak an exam point of view, it is for 1 mark. They will ask like this. But in reality, you have to understand the practical application of it, because this kind of a concept will come next year also. So what is the reason? They'll put a question like this: in steady flow, no two streamlines will intersect, comma, why? So what will be the answer you will write? Because if they
A
do so,
particle
the flow
cannot have two velocities at one point.
at the same instant. That is the meaning. So the fluid particle at that point of intersection will have two directions of flow. This will destroy the steady nature of the fluid. Okay. Second, this point I've already told. The tangent at any point on the streamline gives the direction of velocity of the particle at that point. This I've told, right? Third, greater the number of streamlines passing normally through a cross section of the fluid, larger is the fluid velocity at that section. Let me give you an example, understanding. If I take this example, where is the density of streamlines more? 1, 2, 3. On a comparative basis, where is the density of streamlines more?
In one, sir.
Yeah. What do you mean by density? Am I talking about liquid density? I'm talking about streamline density. Means more number of lines for lesser amount of area. So as per what you told, answer 1 is right. Because if I take this blue color area here, if I take the same blue color area here, if I take the same blue color area here, you can understand that at point 1, more number of streamlines are moving. Point 2, moderate. Point 3, it is less. So the density is more. Now try to read the third point. Greater the number of streamlines passing normally, that is also called as number density. You can make a note of it. So greater the number of streamlines passing normally through a cross section of the fluid, larger is the fluid velocity at that section. Means on a comparative basis between 1, 2 and 3, where is the velocity more? Okay. Last point. Fluid velocity remains constant at any point of the streamline, but it may be different at different points on the same streamline. So what they're trying to say is, if I take only one streamline, at a given point, every particle should reach with the same velocity as the preceding particle. Okay. Whereas if I take different points on the streamline, the velocity at different points will be different. Okay. So try to understand. Velocity of the fluid at a given point is always a constant, but the velocity of the fluid at different points on the streamline is different. So that is the meaning. Okay. So keeping all these points in mind, we are going to discuss about a fluid called as ideal fluid. All these things we can study later. Laminar flow and all we can study later. Okay. So now comes the important concept, that is ideal fluid. Write it down. So ideal means perfect. So perfect fluid means it will not have any kind of flaws in it. That's the meaning, right? So try to understand. When you talk about the motion of real fluids, it is very complicated because, as I told you, see, this is what happens in real time, right? So when this is going to happen, see, these kind of engineering has to be under ocean engineering. People will study who want to design ships and all those things. Okay, it's not our headache as of now. So if you have to study the property of this kind of a fluid motion, it is complicated because the velocity is changing continuously. We cannot apply simple math to solve. Whereas when you talk about streamlined motion, it becomes easy for us. Maybe this can be achieved on a nearby basis. For example, when a liquid is flowing through a tube, on a smaller scale, yes, you can ignore the turbulence because it will not be that great. Whereas here, if it crosses the critical velocity, it is difficult for us to study the turbulent motion. So that's what they're trying to say here. The motion of real fluids is very complicated. To understand fluid dynamics, I told you, right? This part is called as fluid dynamics, means the fluid is actually moving. So to understand the fluid dynamics in a simpler manner, we assume that the fluid is ideal. Okay. So what is an ideal fluid? I told you, right? It will not have any flaws in it. So what is an ideal fluid? It is one of such kinds where it is non-viscous, incompressible, and its flow is steady and irrotational. Means the liquid particles will not rotate. Okay, what are the 4 conditions to be satisfied for fluid to be ideal? It should be non-viscous, means there is no friction. What do you mean by incompressible, guys? So what do you mean by incompressible?
Cannot be compressed.
Okay.
It has definite volume.
Sorry.
It has a definite volume.
Yes. By having definite volume, what other property is it going to have? I told you in the beginning of the chapter. A word that starts with D. Something is constant. You told volume is constant. By volume being constant, something else is constant is also achieved.
Density, sir.
It is density. So wherever you see the word incompressible, you can blindly say that the density is constant. Okay. And it should have a steady flow and a rotational flow. So what are the 4 features? Steady flow. We have told what is steady flow. Incompressible means the density of the fluid remains constant during its flow. Non-viscous, the fluid offers no internal resistance. So an object moving through this fluid does not experience any retarding force. And lastly, irrotational flow. So what do you mean by irrotational flow? This means there is no angular momentum of the fluid about any point. A very small wheel placed at any point inside a fluid does not rotate about its center of mass. So irrotational flow means here the particles do not have any angular momentum associated with them. Keeping all these facts in mind, now we are going to discuss a derivation, which is called as equation of continuity. So this equation of continuity will actually give you the mathematical reason behind why, if the density is more, the velocity will be more. That is what we are going to understand. Okay. So let's talk about this. Okay. Shall I proceed?
Yes, sir.
Now listen. So we will consider a non-viscous and incompressible fluid flowing steadily between the sections A and B of a pipe of varying cross-section. Here the cross-section of the pipe is not constant. So this is the pipe they are trying to talk about. So in this pipe, there is a varying cross-section. Okay, liquid is flowing through it. From where? From left to right. Okay, now comes an important question. So what kind of a liquid is flowing inside it?
Incompressible, sir.
To put it in simple terms, it's an ideal fluid. Okay. You can directly say, consider an ideal fluid which is flowing between the points A and B of whom? Of a tube of varying cross section. Okay. Now listen, guys. If I say the area of cross section here is A1, and if I say the area of cross section here is A2, okay. So you're able to see a cross section, right?
Yes, sir.
So this cross section is there, no? So in this cross section, what will happen is, let's say after time delta t, this cross section has reached this point. Okay, that is, it has traveled this far and it has come. Now tell me, guys, what will be the distance the layer has traveled? The velocity of the layer here is v1. In a small time delta t, what we can say is the distance covered by it is v1 into delta t, because what is the formula for distance? Distance is equal to speed into time. Am I clear?
Yes, sir.
Now listen. So this distance is v1 into delta t, right? Similarly, you can find a layer here which contains liquid inside. Let's say the velocity of this layer is v2. In the same time delta t, here point to be noted is it's not the different times. In the same time delta t, let's say it is at this point. So how much will this distance be traveled by the second particle?
V2 del T, sir.
That's right. Okay. So the area of cross section here is A1. Area of cross section here is A2. Okay. Since you told it's an ideal fluid, it is incompressible. When it is incompressible, what physical quantity is going to be constant? Density is constant, right? So if I take this as 0.1, this as 0.2, can I say density at 0.1 is equal to the density at 0.2? Accepted, guys? So mass at 0.1 divided by volume at 0.1 is equal to mass at 0.2 divided by volume at 0.2. But again, when it is incompressible, can I say its volume is also constant? Right? When its volume is constant, what physical quantity should I change in the last expression?
It would be V alone, sir, not V1.
It is V alone. It is no V. There is no V1 and V2, right? So V will get cancelled. So from this, what can we say is M1 is equal to M2. So this is nothing but mass at point 1 is equal to mass at point 2. So what do we call this as? If something is remaining constant in physics, what is the name we give to it?
Conserved, sir.
Yes. It's conservation of what? What is conserved here?
Mass, sir.
Yes. So this is the principle on which equation of continuity is derived. Okay, you might get this as a 1 mark question. So what is the principle on which equation of continuity is derived? It's simple. It is based on conservation of mass. Make a note of it, guys. Okay. So what is the mass at point 1? Mass at point 1 is equal to density at point 1 into volume at point 1. Right. So from this, I can conclude mass at point 1 is equal to density into volume. Right. So I will call it as volume 1 here. Similarly, mass at second point is what? Del 2 into V2, which implies M2 is equal to rho into V2. See, why I wrote V1 and V2 is because I'm going to mathematically write V1 and V2 in terms of area and velocity, and I will equate it. Okay. Now observe. So from this, can I conclude that rho into V1 is equal to rho into V2? Is there any doubt till this step, guys?
No, sir.
So what is volume at point 1? It is area into thickness, that is D1, is equal to rho into A2 into D2. So from this I can say, so rho will get cancelled. A1 into, what is the distance traveled by this liquid layer in time del T?
V1 del T.
A2 into V2 into del T. So del T will get cancelled. From this I will get A1 into V1 is equal to A2 into V2. And this equation is what is called as equation of continuity. Okay. So area of cross section multiplied by the velocity at that point is equal to area of cross section of the second point multiplied with the velocity at that point. Clear, guys? So you can ask me, when is it applicable? So where do you know how to apply this? You can apply this equation wherever you see liquid flowing through varying cross section, and what kind of a liquid is supposed to flow?
An ideal.
If you see, yes. If you see in a question, suppose in a question they say ideal fluid is flowing through a pipe of varying cross section. By default, you can apply, even without thinking, you can apply the equation of continuity. Okay.
Yes.
So A1 into V1 is equal to A2 into V2. From this, I can conclude that area is inversely proportional to velocity. Okay, that is, just give me a minute, guys. I'll be back. Yeah. So is there any doubt, guys? Area is inversely proportional to velocity, right? So from this, we can understand if the area of cross section of that particular point is small, velocity will be more. So that's why if you observe in the streamline motion, right, there is a point given. Area of cross section is less, velocity will be more. Are you guys able to understand?
Yes, sir.
Yeah. So this is all about equation of continuity. So make a note of it. Okay. I'm going to the next concept. The next concept is energy of fluid in steady flow. So whenever there is a liquid which is in motion, what are all the types of energies we can speak about it? Okay, that's what we are going to see. Based on this, we will see what a theorem called as Bernoulli's theorem, or generally we call it as Bernoulli's principle. Okay, so when a liquid is in motion, what are all the types of energies we know? So when something is in motion, what should it have? Obviously, kinetic energy, right? Second, if at all the liquid is at a certain height with respect to the ground, then it will have potential energy, right? And we know that the liquid is flowing from left to right because of difference in what?
Pressure.
So it is because of the difference in pressure. If the liquid is flowing from left to right, P1 and P2, which side pressure should be more? I've already explained this concept.
Left side pressure should be more.
Left side pressure will be more compared to right. It isn't the liquid can push the right side liquid, liquid on the left side will push the right side liquid and it will move. That's right. So there are how many energies related to a fluid in steady flow? Kinetic energy, potential energy, and pressure energy. First. So what do you mean by kinetic energy? The energy possessed by liquid by virtue of its motion. This is a basic definition, right? So kinetic energy's basic formula is half mv square. But so kinetic energy of any particle is half mv square. But remember, guys, I told you for a liquid it is difficult to define what you cannot define mass. Rather, what can you define? You can define its density. right? So where m is the mass of the liquid and v is the velocity of the liquid. So if at all I want to calculate a parameter like kinetic energy per unit mass of the liquid, it's called as half v square. Okay, and there is a special name for it. Have this in your mind. This is called as velocity hit. That is kinetic energy per unit mass of a liquid is called. Oh, sorry. Kinetic energy per unit mass of the liquid is half v square. Whereas if you talk about kinetic energy per unit weight, then it's called as velocity hit. So half mv square is kinetic energy divided by what is the weight of the liquid? Weight has only one formula. What is it?
mg.
Mg. So m and m will get cancelled. If you are able to define a parameter like v square by 2g, then that parameter is given a name called as velocity hit. Okay. Similarly, if you try to define the kinetic energy per unit volume, okay, it's very simple, guys. Try to understand the naming structure so that you will understand others also better. I need not repeat it. See, kinetic energy basic formula is half mv square. Except, so kinetic energy per unit mass is half v square. Kinetic energy per unit weight is half v square by g. Right? If I define kinetic energy per unit volume, what will it be? Half mv square divided by v. So what is m by v? M by v, guys. Mass by volume is density. So you can define half rho v square. So this half rho v square is called as the kinetic energy per unit volume. Okay. And I told you already, it is difficult for us to calculate the mass of a fluid. Rather, it is easy for us to calculate the density of the fluid. So we will not be defining anything in terms of kinetic energy. Rather, out of all the four options, which one will we prefer? So you have four options to deal with kinetic energy. Out of all the four, which one is more preferred for a liquid?
The last one, sir.
The last one, because density is easy for us to calculate. Right, half rho v square. We always use kinetic energy per unit volume. Okay. In a similar context, I'll ask you the next question. You people guess this. Okay, it's very simple. Suppose I want to do this kind of an operation with potential energy. So what is the basic definition of potential energy? Now we need to ask a question. So what kind of potential energy can be defined here? It is gravitational potential energy. So what is the formula for gravitational potential energy here? It is mg. If I define potential energy per unit mass, what will it be?
GH.
GH.
Yes. If I define potential energy per weight, what will it be?
H alone, sir.
Then what should this H be called as? So if you call kinetic energy per unit weight as velocity hit,
Distance head, sir.
it's called potential hit. Clear? So it's called potential hit. Have that word in your mind. Similarly, if you have potential energy per unit volume, then it will be mgh divided by capital V. M by V is rho. So rho gh will be the answer. Am I clear, guys?
Yes, sir.
Okay. So please make a note of all these points. So these two you have already learned. Kinetic energy and potential energy you have already learned. You need to understand what is pressure energy that I have explained. Has everyone studied thermodynamics in chemistry? Did they start it in your school?
No, sir. In school they didn't start.
School they didn't start. I didn't hear one. Did they start or no? Yes or no? Just tell me that.
No, sir. No, sir. They didn't start in school.
They didn't start. Okay. those who have learned thermodynamics will understand what I'm going to say in this. Even if you have not learned, not an issue, just concentrate on what I'm going to tell. The next type of energy I'm speaking about is pressure energy. So pressure energy is generally represented by the, so actually there is no symbol for it. Yeah. So pressure energy, what is this? So what do we mean by energy? I have already told you many times. Energy, wherever you see this word, energy throughout science, what comes to your mind? Energy means the capacity to complete the do work, right? So energy means whatever work we are doing or whatever work is being done on us will get stored in some form of energy. Okay, that is the meaning. So what I'm going to do here is, if I take a small beaker, okay, inside, let's say I'm taking a liquid, okay, and it is the beaker is fitted with a piston, and you're applying a pressure from the top. Okay, if you actually look at the piston from the top, it will be circular. So what I will do is I will take the piston like this. Okay, this is piston. So when the liquid, let's say due to the pressure, has got displaced by a distance of delta x. Okay. If you don't want liquid, since we are dealing with ideal fluids, let's talk about some gas. Okay. So you're applying a pressure from the top and it has got displaced by a distance delta x. Okay. Let's say the force that you apply is F. The area of cross section of this piston is A. So what is the work done by the force? Work done by the force is F into delta x.
Yes, sir.
Okay. So what is F? F is nothing but pressure into area into delta x. So area multiplied with distance will give you what? The cross sectional area multiplied with thickness will give you what? We already used this concept in the previous derivation. It gives you the area of cross section multiplied with thickness. What is it?
Volume, sir.
Students, are you able to hear me?
Yes, sir.
I had power cut here, just connected to my hotspot. Just give me 2 minutes, okay? So I was asking you a question. What do you mean by cross-sectional area multiplied with H?
Volume, sir.
It's volume. That's it. So here, what is going to happen is, so pressure into area into del X is going to give you del V, and this pressure multiplied with change in volume is the work done, and this is what is called as pressure energy. Why we call it as pressure energy is because this is the work done by the pressure to compress a volume of delta V. Clear? In a similar way, you can define other parameters. I'll show you here itself. So pressure energy of volume is called as PV. So if I define pressure energy per unit volume, then what is it called as? So pressure energy per unit volume is volume and volume will cancel. P will be the answer. So that's just called pressure energy per unit volume. So remember, pressure energy per unit volume is nothing but pressure. Similarly, if you define pressure energy per unit mass, then what will you get? You will get P divided by rho. Then what will that be called as? So sorry, there is no name for it. Similarly, if you define pressure energy per unit weight, then that is what is called as pressure head. So pressure energy is PV divided by mass. So this V will come down. M by V is rho. So P divided by rho is what is called as pressure energy per unit mass. Similarly, pressure energy per unit weight is called as pressure head, which is P divided by rho G. Clear, guys? Are you clear?
Yes, sir.
Okay. So these are all the energies we are going to discuss in Bernoulli's theorem. Let's look at the statement alone, then you will understand what is the importance of it. So Bernoulli's theorem states that the sum of the pressure energy, kinetic energy, and potential energy per unit volume of an ideal fluid is always a constant. Okay. So you need to understand what is pressure energy, kinetic energy, and potential energy per what? Per unit volume. So you need to know the formula. So kinetic energy per unit volume is half rho v square. Pressure energy per unit volume is rho gh. Sorry, potential energy per unit volume is rho gh. Pressure energy per unit volume is nothing but pressure. So that's what they have written in the mathematical statement. This is what we are going to prove tomorrow. Okay. In the next class, we will prove this. Till here, I want you all to revise it. Is it clear?
Yes, sir.
Just wait for a minute.
Yes, sir.
Just wait for a minute.